Calculate the wavelength of light in vacuum that has a frequency of 1 times 10 to the 10 to the positive 14th. And what is the wavelength in benzene with an index of refraction of 1.501? Then calculate the energy of 1 photon of such light in vacuum. Express the answer in electron volts. Then D, what is the property of and effect on the energy of the photon when it enters the benzene? So for part 1, we're going to use velocity is equal to the wavelength times the frequency. And then we're going to define the velocity in a vacuum is equal to c. So c is equal to the wavelength times the frequency, or if you want, you can put the Greek letter nu for frequency. I prefer f because I have sloppy handwriting. Now we want to know what we want to know what the wavelength is, and so what we'll have to do is divide by the frequency. So c over frequency is equal to the wavelength, and the speed of light in a vacuum is 299,792,458 meters per second, and so we can substitute that in for c. The frequency that we're given in this problem is 1 times 10 to the 14th. So right here we'll put 10 to the 14th as our frequency, and just by plugging in those numbers in the calculator, you should get that your wavelength is equal to 2.99 times 10 to the negative 6th meters. And that's part A. Then it says, what is its wavelength in benzene? The index of refraction is 1.501. And so, let's do it like that. So if we use Snell's law, basically it defines the index of refraction is equal to the speed of light in a vacuum to the speed of light going through some other substance. Our substance is benzene, so the index of refraction for benzene is equal to the speed of light divided by the velocity in benzene. Then we can solve for the velocity, so we can say that the velocity in benzene is equal to the speed of light divided by the index of refraction. It tells us what the index of refraction is. It says that it's equal to 1.501, and the speed of light we got is 299,792,458 meters per second. And so we have the velocity in benzene, and so we can use the velocity. The velocity is equal to the wavelength times the frequency. It's asking us to solve for the wavelength, and so we have to know what the frequency is. Well, we know what the frequency of light is in a vacuum, so what happens to the frequency when it goes to another substance? Let's just look at basically what we can deduce from Snell's law. If I have something that has a wavelength and a certain frequency, once it hits this thing, its frequency is going to stay the same. It's going to come out this side with the same frequency. If it didn't come out the other side with the same frequency, that means that the waves would be piling up on this end. And if they piled up on this end, what would happen is they'd start canceling each other out part of the time, and then other parts of the time they would start amplifying each other. And so you would have basically like beams of light coming out on the other side. So the frequency has to stay the same. So if the wavelength changes, that means the velocity has to also change. So the velocity, we decided it does change. It changes from what it is in a vacuum to what it is in some substance, benzene. So if the velocity is changing but the frequency isn't, then the wavelength has to change. But we can assume for everything that the wavelength stays the same, and it tells us what it is in the part 1. It's 1 times 10 to the 14th. So if we want to know the wavelength, we just do the velocity divided by the frequency. And in our case, velocity is equal to c over n, so c over n times f. Now for part C, it asks us to calculate the energy and express it in terms of electron volts. So we're going to do this really fast since we did the same thing in question 1 and 2. And so if you're having trouble with this part, go back and review video for question 1 and 2 of this same chapter, chapter 22. And so the energy is equal to Planck's constant times the frequency. It gives us the frequency of 10 to the 14th. Planck's constant is it's 6.62 606,957 times 10 to the negative 34th. And so you just plug those in. Energy is equal to 6.62, I'm going to shorten it here, times 10 to the negative 34th, times the frequency is 10 to the 14th. That will give us units of joules as our answer, because the frequency is in units of per seconds, or you could say seconds to the negative 1, and the Planck's constant is in units of joules times seconds, so seconds cancel out, and you end up with joules. And so you convert that to electron volts. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. And so you just basically you plug in is equal to x electron volts divided by the number of joules that you got, which in our case was equal to HF. Multiply HF to the other side, so you get HF times 1 electron volt divided by 1.6 times 10 to the negative 19th joules. That will give you x electron volts. And in my case, that would be equal to 0.414129348 electron volts. Now the last question says, what is the property of and the effect on the energy of a photon when it enters the benzene? Select all that apply. So whenever the photon enters the benzene, the wavelength changes. There's a change in wavelength, but there is no change in frequency. So if we say that the energy is equal to the Planck's constant times the frequency, if the frequency does not change, the energy does not change. So for first part, energy does not change. It changeth not. And second of all, we see from this equation that the energy is proportional to the frequency. So the energy is proportional to the frequency is part 2. Energy is proportional, that's the sign for proportional, to the frequency. Hey, thanks for watching. Make sure you check out my blog. The link is down in the About section of this video. And on the blog, you'll find cool stuff like other videos for the same chapter. And you'll also find little download links where you can download calculators to basically just punch in your numbers and solve these exact problems. So you won't even have to watch the video if you don't want to. The last thing I want to say is if you leave comments on YouTube, of course I will get around to responding, but I'm much faster if you leave them at the bottom of my blog, right down there. Enjoy your day.